You got it. Lewis structure for hydrogen fluoride. Yep. Easy peasy. Okay. Next one, Caleb.
Switch the F for an I.
Switch the F for an I. So these are called Lewis structures, Lewis dot structures, Lewis diagrams. Any given day I'll use any one of those, okay? What I want you to do now, calculate the difference in electronegativity between the H and the F and the H and the I. Electronegativity. Put in your bond dipoles. Did we talk about bond dipoles yesterday? Yeah. A little bit positive, a little bit negative, or like that? Did we do this? We didn't get this far? Oh, how mean of me. Okay, that pair of electrons is not shared equally. Who's got the biggest pull? Fluorine. 4 is much bigger than 2.1. So, what type of bond is this? Is it pure covalent? Non-polar covalent, polar covalent, or very polar covalent with ionic characteristics? Don't guess, look at your sheets. It's written down. Yeah? Ionic characteristics. So we're going to say it's very polar covalent. Has ionic characteristics. Is this an ionic compound or a covalent compound? I'm going to pause for a second. HF. We know it's covalent because there's 2 nonmetals. So this bond is very polar, which means this pair of electrons are much closer to fluorine than they are to hydrogen. Much closer. So we have a polar covalent bond. What we have is what we call a dipole. A temporary unequal distribution of electrons. Okay, temporary unequal distribution. So one of these is a little bit positive, one is a little bit negative. Which one do you guess is going to be a little bit negative? You have a 50-50 chance of getting it right. 50-50. Fabian? Who do you think is negative? H or F? Pick one. Yes. Because it's pulling strongest. So that fluorine has pulled those electrons into itself. So it is most electronegative. So the electrons are being pulled towards fluorine. So you show it 2 different ways. You can show it a dipole, a little bit positive, a little bit negative. Those are Greek symbols. Or, better yet, especially if you take physics, you draw an arrow showing the direction the electrons are being pulled. You cross the end of it, so it makes a little plus sign. So the electrons are getting pulled towards fluorine. Hydrogen is a little bit positive. Okay? And this is very useful. This is going to help you figure out if the structure is polar or not. Okay, HI. Difference in electronegativity is 0.4. Type of a bond is it? Nonpolar. It's a nonpolar bond. There are no bond dipoles. You can only have bond dipoles if you're polar covalent or with ionic characteristics, okay? Write that down. Non-polar covalent bonds do not have bond dipoles. Bond dipoles exist only in polar covalent bonds or very polar covalent ionic characteristics. So it has to be 0.5 or greater. Your difference in electronegativity is 0.5 or greater to actually have a bond dipole. Bond dipole is just a temporary misdistribution of electrons. Do you remember what I said before? Say that. This is an electron. So we just formed a bond. So here, you're right between us. I have a bigger pull towards me. I'm a little bit negative. My dipole's negative. You're positive, but not completely positive. It's not like an ion. When you take your electron, I'm just hogging it. Yes. Yes. Yeah. Yes. Okay. A little bit. I've got it. Yeah, you're off balance. I've got it, but I don't have it. Yes. Yes, it's only a little bit because I'm grabbing it and I'm pulling it, but I haven't ripped it out of your hands. Okay? Difference in structural formula shows just the elements and the bond. Okay? This is called hydrogen monochloride or hydrogen chloride. When we have our hydrogen compounds, we tend to drop the mono. It's another one of those rules about rules. So at the bottom, underneath the table, calculate the difference in electronegativity between hydrogen and chlorine. So your dipole shows for that bond who's got the biggest pull. So which atom is a little bit positive, which one's a little bit negative. What do you know about acids? Think about an acid for a minute. They all have the formula with an H. What do acids give up when they react? What do they produce? Remember this from last year? Which ones? No? That's if it's reacting with something. But what, by definition, do all acids make? All bases make OH minus, the hydroxide ion. What do acids make? H plus. H plus. It's a little bit positive, so when you put it in water, it can pop right off, leaving its electron with chlorine. That's why acids can give up their H's and leave their electrons behind because this one's pulling on the electrons so much. This right now is not an acid. It's a covalent compound. We're going to add it to water. Then it's nice. It has AQ. AQ. That's an acid. It's dissolved in water, right? This does not have that subscript, so it's a compound. That's a really important distinction to make. If the subscript is not AQ, it's a compound, a covalent compound. It is not an acid. Here, it's an acid because it's got the AQ. This would be a G for a gas. So this is a covalent compound. This down here is your acid. Differ only by the subscripts. The details, you've got to pay attention to details. And they're often very minute, but they're so important, okay? So very important. All right. Does that help? If not, I will come back to it after. All right. Good. Okay, lone electron pairs take up more space than bonding pairs. So, water does not look like this. That's not how you're going to draw it. This is how you're going to draw it from now on. That's your Lewis structure for water. If you have two lone pairs on your central atom, you're going to draw it with this shape. We call this bent, or V, because upside down it makes a V. And those are actual names for the shape. So that's the Lewis structure for water. Structural formula, keep the shape. Keep the shape. And then the name is water, obviously, or dihydrogen monoxide. Well, it's been funny because people have posted the safety data sheet for dihydrogen monoxide, and people have been like, oh my God, it can kill you. And it's true, water can kill you. I mean, yes, you can drown in water, but you can actually die by drinking too much water.
How much is it?
I don't know. My guess is it's going to depend on your body weight and therefore your body volume, but there have been cases where people at raves have taken ecstasy. Ecstasy makes you really thirsty. They consume a lot of water and they actually die because they drank too much. Remember I was talking about that sodium and potassium pump? You're washing it out. So your cells stop functioning properly and your body just shuts down. 8 cups of water is not going to kill you. Okay, so they say you should drink 8 cups of water a day. That's not going to kill you. Drinking 80 liters, yes. Okay. So the shape is really important for water. Okay, calculate for me the difference in electronegativity between H and O. What is it? Josh? 1.4. Caleb, is that polar or non-polar? It's polar. So we've got a difference in electronegativity of 1.4. That means we have bond dipoles. If we did it like this, instead of like this, you'll see that the dipoles cancel out. Who's got the biggest pole, oxygen or hydrogen? Oxygen. So when you draw your vectors in, Now, some of you are taking physics, and you're going to be talking about vectors. Dipoles are like vectors when you draw them like this. So when you add two vectors together, the head of the first one is attached to the tail of the second one. This is linear. So it's 1.4. So if I took 1.4 this way, and I added the other one to it, I'm taking 1.4 backwards. I end up exactly where I began. Cancel. This one, if I add this one over here, the tip of my pen represents where you end up. So you have a net dipole. You have, if I add this one up here, this is where I end up. This is called a net dipole. And we're going to talk a bit more about these later. So there's a net dipole. If you have no net dipole, you're nonpolar. If you have no dipoles, you're nonpolar. If you have a net dipole, you are polar. Water is an amazing substance because it is so polar. It can dissolve more things than anything else. It's called the universal solvent. It can dissolve so many substances more than anything else. So we know this is not the Lewis structure for water. It's not the Lewis structure for water because it ends up being nonpolar. This shows you that it's polar overall. So, wrong. That's why it's wrong. I just proved it to you. It's a polar substance, okay? You're going to be in a position, possibly by the end of the week, maybe next week, you're going to be able to draw Lewis structures for stuff you have no idea what it is. You'll be able to put on bond dipoles and tell me if the substance is polar or not. You will be able to do this, okay? I promise. All right. Last one, CO2. I will teach you tomorrow how to draw Lewis structures, but for now, just believe me. How many bonds can carbon make? 4. There's only 2 atoms, so it's going to make 2 to each. This is correct. So there is your Lewis structure for CO2. If you were going to connect the O to the C to the O, what shape would it make? Yeah, you did.
No, I didn't.
Yeah, you did
I
that.
promise I didn't.
What shape is it?
I could even do
A line? Yeah. A line. A bendy line or a straight line? A straight line. Well done. It's linear. It makes a straight line. Okay. Structural formula. Structural formula. Just show the bonds. And its name, of course, everybody knows this. We all breathe it out. Carbon dioxide. Okay. What is the difference in electronegativity between carbon and oxygen? 1. Who's got the biggest pull? Oxygen. It's greater than 0.5, so they're polar covalent. Now this one, because it's in a straight line, because they go in opposite directions and they're equal amounts, they're going to cancel. So carbon dioxide has polar covalent bonds, but is nonpolar. Your dipoles cancel. Dipoles cancel. Okay, properties. Properties of covalent compounds. They will not conduct electricity. Okay? Will not. When you melt them, where they dissolve them in water, they will not conduct electricity. So we call them non-electrolytes. They have low melting points and low boiling points, which tells you the forces of attraction are not that strong. Ionic bonds, high melting points, high boiling points, very strong forces of attraction. So something's very different between the two types of compounds. This is a covalent bond. It's extremely strong. If I melt CO2, I don't change this. It stays as CO2. What's happening is you're breaking them apart from its neighboring CO2, okay? They evaporate readily. You guys have all used hand sanitizer. It's got alcohol in it. You rub it all over your hands. It feels like liquid, and then it's gone. The heat from your hands has evaporated it, hopefully without germs. What's that? That's how it works. It sterilizes your hands. It's not good for your hands. You shouldn't use it all the time. What happens if? Then it just stings. Alcohol's like a good detergent, like it cleans. It'll hurt. How many of you shave? Shave your face. How many of you put aftershave on? Often some people use rubbing alcohol. Yeah, it stings, but it stops any bleeding, cleans your face. Some people do it, and sometimes aftershave actually has alcohol in it. Many, but not all, are not soluble in water. A lot are. The bigger you are, the more carbons you contain, the less likely you are to be able to dissolve. And the solids are usually soft. Some of them are actually not even solids, right? You've got solids, liquids, and gases. But often the solids are quite soft to touch. All right. Turn your note over. I'm going to show you just two more things, and then I've got some questions for you. I can remember where I put your questions. Do you remember how we had this is a Lewis structure of an ionic compound, this is how it forms? So if I ask you to show how it forms, you're going to draw it one way, and only the product. If I ask for the ionic structure, Lewis structure. So this is how to draw how a covalent molecule forms using Lewis structures. So we'll do it for hydrogen bromide. Hydrogen has one valence electron. Bromine has 7. That electron is going to come over here between them, but not over to bromine. And we will make a covalent bond and have 3 lone pairs of electrons. So the whole thing is showing how it's formed. This is the Lewis structure for your product. Sometimes, most of the time, actually, I'm going to ask you for the Lewis structure. Occasionally, I'm going to say, show me how it forms. Okay? Most of the time, I'm just going to go for the product. Thank you. Okay, so nitrogen has a lone pair of electrons here at the top. Along comes a hydrogen ion who has lost its electron. Nitrogen can donate both electrons to this hydrogen. You can't tell which one it is. They look the same, they're the same length. So now we have the ammonium ion. So that's a coordinate covalent bond. One atom here, it's nitrogen, so you have to have a lone pair of electrons. We'll donate to something that has none, like an H+, and you'll form another bond. That's it.